Welcome to TalkTensors, where we dissect cutting-edge machine learning research. Today we're plunging into local look-ahead guidance via Verifier-in-the-Loop for automated theorem proving.
Sounds pretty technical.
It is, but automated theorem proving by AI, well, it might seem like a really niche area of ML, but honestly, its potential impact on the rigor and reliability of science and engineering is just massive.
Well, absolutely. For decades, getting machines to do deductive reasoning at the level you need for actual mathematical proofs, that's been a huge challenge.
Yeah.
And recent AI has made strides, sure, often through reinforcement learning, training agents by trial and error in these massive computational spaces.
Or using huge data sets of human proofs.
Exactly. Or learning from enormous data sets of human annotated proofs. But these methods, they're incredibly compute hungry.
Yeah, I bet it.
Plus, when a proof attempt just fails, maybe right at the very end, figuring out where it went wrong and giving useful feedback, that's a massive hurdle. It's that sparse reward problem we see a lot in RL.
Exactly. And this paper, it offers a really quite elegant solution to that inefficiency problem.
Okay, how so?
Well, instead of waiting for the final yes or no on a, completed proof, they've integrated this powerful automated verifier called Lean.
Lean. Yes.
To give feedback at each and every step of the reasoning process. So think of it like having this constant, meticulous reviewer checking every logical step is sound, not just checking the final answer.
That is different. What's really innovative there is changing when and how that verification happens. Other methods use systems like Lean or Coke too.
Right, but usually at the end.
Usually to validate the entire proof after it's been generated, Often by an RL agent or some model trying to mimic experts. This work, it's about getting that crucial feedback much, much earlier, at the level of each individual tactic the AI tries.
And the core finding seems pretty compelling. This step-by-step, this local verification guided by Lean, significantly boosts both the AI's ability to prove theorems and the speed it takes to do it. Okay, let's really dive into the specifics of how they pulled this off.
Right. So the paper kicks off by stressing this growing intersection of machine learning and scientific fields, where automated theorem proving is, it's becoming increasingly important.
Makes sense.
They talk about the current scene, where you've got reinforcement learning and expert iteration methods inspired by things like AlphaZero being used to train models to navigate the really complex world of mathematical proofs, often with final checks by systems like Lean and Coke, as we said.
And they acknowledge RL can be data efficient sometimes in ML, but they really hammer home the substantial compute cost and these long training cycles you often get when applying it to ATP.
Yeah, it's partly because you have to generate these complete proof attempts, they call them trajectory rollouts, before you even get a signal saying, yes, that worked, or no, that failed.
It's a bit like trying to learn, a complex dance routine and only finding out at the very end if you messed up the first step.
Exactly. That's a good analogy.
Yeah.
Then they bring in Reprover. This was like a more streamlined approach based on supervised learning.
So learning by example.
Pretty much. Learning by imitating existing human-written proofs and retrieving relevant mathematical facts or premises to help build the proof. The key bits here are the theorem you're proving, the tactics, those are the individual proof steps or actions, the premises used to justify those steps, and the current proof state, which includes, any remaining sub-goals you still need to prove to finish the main theorem.
And Reprovers, it showed promise, right? Lower compute demands, which is a big plus.
Definitely. But the researchers found this recurring issue. Recruiters often suggested tactics that either broke Lean's strict syntax rules or just weren't applicable to the current proof stage.
Okay. So dead ends.
Right. And this really bogs down the beam search process during inference when the model is actually trying to prove something new because it wastes time and resources exploring these invalid paths. The model might suggest, say, 5 tactics, but maybe 3 of them are just non-starters.
So that inefficiency with Reprover, that's what really motivates their main idea here.
Exactly. Fine-tuning this pre-trained Reprover model by using that immediate feedback from Lean at each step. The analogy they make to feedback-based alignment in things like code generation or preference optimization or RLHF, reward model.
Like a whole area.
It's quite insightful, I think. It's about steering the model towards better actions by giving signals right at each decision point in the proof. They mention methods like direct preference optimization, DPO, and group reward preference optimization, GRPO, as sort of more efficient ways to do this preference learning.
And they also point out, correctly, I think, that in math reasoning, the whole sequence of steps, the trajectory really matters, not just isolated steps.
True, but trying to figure out preferences over entire proof trajectories, that gets computationally very complex very fast.
Which leads us neatly to their main contribution, Lean On Listener.
Exactly, Lean Listener. It's this novel framework they designed specifically to fine-tune a pre-trained model reprover, in this case using that stepwise feedback directly from Lean during the training, to optimize the model's policy, its strategy for picking the next step.
And the reward mechanism inside Lean Listener seems pretty intuitive.
It is. An invalid tactic gets a negative score, an applicable one gets a positive score, and this is crucial. There's also a reward based on the progress the tactic actually makes, specifically how much it reduces the number of remaining unsolved subgoals.
Okay, so a reward's making actual progress, not just valid moves.
Precisely. And they chose to use Group Reward Preference Optimization, GRPO, for the RL training part. They found it worked better than DPO for this specific ATP context.
What's really interesting, too, is the data efficiency they seem to get with this.
Yeah, by sampling potential tactics and getting that instant validation from Lean, the system can kind of automatically discover and add new valid tactics to its own knowledge base during training.
So it learns on the fly.
Pretty much. This local look-ahead strategy cleverly avoids the headache of evaluating whole proof trajectories. So they basically set up this really efficient training loop where Lean strictness directly guides the model to suggest better proof steps, just one step at a time.
Okay, so moving to their discussion of related work, they give a pretty thorough overview of ML in automated theorem proving, don't they?
They do. They cover various angles, generating whole proofs, finding the right premises or tactics sequentially, even helping formalize math statements. They cite a lot of relevant projects and really stress how vital systems like Lean and Coke are in this whole field.
And they mention ML being used for premise selection, finding the right building blocks, things like Thor and the Lean Dojo environment.
Right. And they also get into the challenges of proof search and picking tactics, referencing work on RL, expert iteration, hypertree proof search. They also flag the difficulties of just applying standard RL to ATP, like the huge action space, all the possible tactics, and no natural opponent like in games.
The rise of transformer LLMs in this space gets mentioned too, GPTF dilemma.
Yep. And then they draw this really key distinction between their stepwise feedback approach and methods like, say, DeepSeek Prover. That one tries to generate whole proofs and then uses Lean for verification, often using GRPO, but with feedback on the entire proof.
Whereas Lean Listener integrates that verification feedback at every single step during the training itself.
That's the core difference. Finally, in that related work section, they place their use of preference optimization methods like DPO in context. They explain DPO optimizes directly based on preferences, no separate reward model needed, and they really highlight the novelty. Using the automated theorem prover, Lean, to provide this preference feedback at each individual step. They link it to process-supervised reward models, which is different from just looking at the final outcome.
Okay, let's dig into the Lean Listener methodology itself. They frame theorem proving as a Markov decision process, an MDP.
Right, which is a standard way to formalize sequential decision-making. It gives you states, the proof states, actions, the tactics, transitions between states, and rewards.
And they clearly lay out the interaction. The AI agent suggests a tactic for the current proof state.
And Lean checks it. It either accepts it as valid and applicable or rejects it. And it also tells you how many goals are left to prove. They stress again, Lean's strict syntax rules are key for this immediate feedback loop to work reliably.
The idea that a proof state can have multiple sub-goals is important too, isn't it?
Absolutely. Because a single tactic might solve one or more sub-goals, but it could also introduce new ones. So the immediate impact isn't always straightforwardly positive. The model's main job is predicting the best tactic for the current state, and as others have found, giving it relevant premises helps a lot with that prediction accuracy.
And during inference, when it's actually proving a new theorem, it uses beam search.
Yeah, exploring multiple proof paths at once, keeping the most promising ones. It talks to Lean at each step. If a tactic leads to an error, the model just explores other options in its beam. This really highlights the challenge they're tackling, the mismatch between initial supervised training on static proofs and the dynamic process of actually proving something new.
And Lean Listener is their fix for that mismatch.
Exactly. It's designed to align the pre-trained model's actions with Lean's guidance step by step, needing just that one step look ahead. The feedback, is it applicable? How many sub-goals did it solve? That's used to score how good each tactic was.
And the reward strategy is key here. Rewarding tactics that are applicable, syntactically correct, and solve more sub-goals. They tried DPO first.
They did. They created data sets, pairing tactics preferred applicable versus dispreferred rejected. They even tried different ways of making those pairs.
But they ended up favoring GRPO.
Correct. Group relative policy optimization. It assigns a reward to each tactic based on how many sub-goals it helped resolve. They found that worked better here. They give the details on the GRPO objective function, how the advantage for each tactic is worked out based on normalized rewards within the beam. And interestingly, they use the pre-trained reprover as both the starting point and the reference policy for the optimization.
Okay, let's talk data curation. They used the Lian-Dojo benchmark training split, right? Smart move to avoid contamination.
Yeah, very standard practice. And they really emphasize this online training approach. The model generating tactics during training is updated regularly every 50 iterations, they say, based on its own recent performance and Lean's feedback.
They tried offline training too.
They did on a pre-collected set of tactic feedback pairs, but found online was much better. It really shows that continuous interaction with the verifier is crucial.
How did they generate the data for this online training?
Well, they parsed existing human proofs. Then, at each step in those proofs, they used beam search with a width of 8 to sample potential tactics the model might suggest.
Okay.
And importantly, they always added the actual human written tactic, the ground truth, if it wasn't already in the beam. So effectively with 9. Then, for every single one of those proposed tactics, they got feedback from Lean.
And for the DPO runs, they built those positive-negative pairs from that Lean feedback using their different strategies. And they did some data augmentation too.
Yeah, randomly dropping out some premises from the input prompt to make the model more robust. For GRPO, the dataset was built dynamically during training. Tactics got scored based on solving sub-goals, and the model doing the sampling got updated as it learned.
And the actual training itself, fine-tuning reprover for 10K steps.
Using standard stuff, Atom W optimizer, small learning rate, batch size 16, but the compute cost wasn't trivial about 40 A100 GPU days. That gives you a sense of the scale here. They used the Hugging Face TRL library, which is pretty common.
Right, so the experiments. Goal was testing Lean Listener on Lian-Dojo, the random split, and the harder novel premises split.
Exactly. They looked at 3 main things. Did the tactic quality improve? What was the overall theorem proving performance? And was it faster?
So at tactic validity first, what did they find?
Well, the results shown in a table in the paper were pretty clear. Offline DPO didn't really work, but online DPO, and especially GRPO, significantly boosted the percentage of valid tactics the model generated, and it reduced those steps where the model just couldn't find any valid tactic. And another interesting point, the average length of the valid tactics actually tended to decrease in the best models. Suggests it was learning more direct, efficient steps.
Okay, but did that translate to proving more theorems overall?
Yeah.
Pass it one metric.
This is where it gets nuanced. Online DPO improved tactic validity, yes, but paradoxically, it led to a slight decrease in the total number of theorems proven.
Why?
Their guess is maybe some spurious correlation in the DPO data between tactic length and validity messed things up. But GRPO, with its better reward signal focused on solving sub-goals and its online training, did lead to a noticeable increase in proven theorems. It was more effective overall.
And what about speed? Inference time.
They have a graph showing Lean Listener consistently proved more theorems in the same amount of time compared to the baseline reprover. Sometimes it hit the same performance level as reprover, but like up to 20% faster. That's a pretty solid efficiency gain.
Significant, yeah. And proof length. Did Lean Listener find shorter proofs?
Generally, yes. Their analysis showed Lean Listener tended to produce more concise proofs, fewer steps to get to the answer, compared to the original reprover.
But there was a caveat.
A slight one. They noted Lean Listener did really well on theorems solvable in one step, but its performance dipped a bit on more complex multi-step proofs. This might suggest, as they point out, that the one-step look-ahead training could be a bit limiting for really intricate, longer chains of reasoning.
Okay, so wrapping up our analysis of the paper itself, they've presented Lean Listener, this novel RL framework, using external verifier feedback, Lean to boost LLMs for ATP.
Right. And the key is that stepwise approach, considering not just if a tactic is applicable, but its immediate impact on solving sub-goals.
And it harnesses that trajectory-level guidance efficiently without the massive cost of evaluating whole proofs.
And the results back it up. Better success rate, faster proving speed compared to the baseline.
Definitely a compelling piece of work. Okay, let's shift gears to our novel notion segment. Where could this research go next?
Well, they really showed the power of this granular, stepwise feedback from Lean during training. So one thought I had was, What if we could make the granularity and frequency of that feedback dynamic adaptive?
Interesting. So not feedback on every single step. Tell me more.
Yeah, imagine a system that doesn't necessarily ping lean after every single tactic. Maybe it could learn to gauge the model's confidence. If the model's cruising along, generating valid, progress-making steps consistently.
Maybe you ease off on the verification. Save some compute.
Exactly. It's a bit like how a human learner needs constant checks when they start, but less so as they get better.
Makes sense. Like an experienced driver needing fewer directions. How would you even implement that kind of dynamic feedback?
Well, you could maybe train a separate meta-controller model. It would watch the proof state, the recent tactics, the feedback history, and its job would be to predict when and what kind of feedback the main prover model needs most.
Ah, okay.
So if the main model starts generating iffy tactics or seems stuck, the meta-controller triggers more frequent, maybe more detailed checks from lean.
So a learning system that learns how often it needs checking. That's pretty meta. What are the potential wins there?
Efficiency, for sure. Fewer calls to the verifier means lower training cost. But maybe more interestingly, this kind of adaptive strategy could make the models more resilient on really hard proofs.
How so?
By not being constantly micromanaged on the easier parts, the model might develop a better grasp of the overall strategy. Then, the intensive feedback gets focused where it's truly needed, on the genuinely tricky steps. It reminds me a bit of curriculum learning, gradually increasing difficulty, or active learning, where the system asks for the information it needs most. If it worked, you might get ATP systems that are even more efficient and robust for complex problems.
That's a really cool direction. Okay, my second novel notion kind of branches off from the reliance on the purely formal verifier, lean. Lean is great for correctness, obviously,
But doesn't necessarily guide towards elegant proofs or human-like reasoning.
Exactly. What if we could find ways to bring in guidance from informal human-written proofs during training?
Okay. How'd that work?
Maybe develop another model using NLP that analyzes the high-level strategies in informal proofs. You know, when a human proof says, apply theorem X here, or consider the case where.
Right, the conceptual leaps.
Yeah. This guidance model could then suggest related formal tactics to the main prover, even if lean's local feedback isn't immediately pointing that way.
Wow, okay. Trying to bridge that gap between human mathematical intuition and the strict formality needed for verification, how would you translate those high-level ideas into concrete, formal tactics? That sounds hard.
Oh, definitely a huge challenge. You'd probably need big advances in understanding and formalizing informal math language, maybe using NLP and knowledge representation to pull out the key strategies and intent from human proofs. This extra guidance layer could then sort of nudge the main prover's tactic selection even before lean gives its formal thumbs up or thumbs down.
So the main model gets signals not just from lean's immediate check, but also from this kind of distilled human intuition translated into formal steps.
Precisely. The payoff could be significant. Maybe the model finds shorter, more elegant proofs, closer to how mathematicians think. It might even help tackle theorems where that purely local feedback isn't enough to find a creative solution.
Integrating that informal guidance.
Yeah.
That could really push the boundaries, leading to maybe more powerful, more intelligent theorem provers.
They're definitely speculative ideas, but potentially exciting avenues. As always, we really encourage everyone listening to check out the original paper for the full details on this fascinating work. The link's in the description. It certainly leaves us thinking about the future of AI in both verifying and maybe even discovering new mathematics.